interference in thin film. So first of all, what is thin film in the context of interference? So actually, thin film is an optical medium, optical medium in, is called thin film when its thickness is about one is about order of one wavelength of light in visible range. That is called a thin film in the context of interference. So typical dimension, it is that is point micrometer to 10 micrometer. This is the typical thickness of a thin film in context of interference. Example, any kind of sheet of transparent film. So thin transparent sheet of glass mica, এটা হতে পারে an air film enclosed between two plates, or a soap bubble. So these are the example. Example of a thin film. Here the incident light beam is incident on the top of the surface, and some part of it get reflected in this direction, and major part of it is transmitted. And again the transmitted light reflected here get a reflection at the point and goes to this direction, and also from this ray there is a transmitted light and there is a reflected light. So now look at calculation. The amount of light that is reflected and that is transmitted. For example, if we take the glass plate, this is a glass. Glass is a material whose suppose glass thin film, glass thin film. That is a film made by glass. That is mu is equal to 1.5. So the reflectivity R is nothing but mu minus 1 mu plus 1 square, that is 1.5 minus 2, 1.5 plus 2 by 1, that is 0.04%. So here we see that only the 4% of the incident light get reflected here, and 96% light will be transmitted in the direction. And among the 96%, the almost 4%, that is 3.65%, will be reflected at the point here, and will go to in this direction, and 92% light will be transmitted in this direction. So here we see that after successive reflection, after this is first first reflection within the film. So after second reflection within the film, the transmitted line in the direction is very low, and also the intensity of the light in the direction also very low. So what the effect what will get here and also here, or due to the first two reflection, and in the also this is true for this direction. So the reflection for higher order can be neglected easily. So here one thing is to say that the light beam is divided into two parts, that is reflected light component and that is a refracted component. So we can write that each reflection the intensity, and hence the intensity and hence the amplitude of light wave is divided into the reflected component and the refracted component. And both this component, travel different path and subsequently overlap to produce will be produced by this overlapping, that is interference. Therefore here we can say, we have seen the interference in thin film is called interference by dividing interference by division of amplitude of amplitude. So here the amplitude divided. Okay, let's go. Now the topic is the plane parallel film. So what is this? That is a transparent thin film of what? Of uniform thickness if thickness bounded by two parallel surfaces is known as a plane parallel film. Okay. Let us consider a transparent film of uniform thickness T. The thickness of the film is T, bounded by two parallel surface, this surface and that surface. Also, the refractive index of the film, the material of the film, is mu. That is the in this region are air. So the light beam is incident on the surface at point B and making an angle I, the angle of incident I, and this light is transmitted in this direction and also reflected point F and makes the angle R with the normal of the surface, that is FG. And again this is reflected in this region and transmitted as a DE ray, that is ray 2. So here you see that if I compare in this region compared to light particular in this region, then this portion is traveling more length compared to the ray 1. So how much it is? That is, so from that place if I draw a perpendicular from D to H, then this distance and this distance are the same. So this that direction length minus that length plus that length minus that length is the path difference. So we want to calculate the path difference. Okay, so let's calculate the geometrical path difference. Let DH normal to BC. The path BH travels in air while the ray BD actually BD, that is BF, from BF to FD. BD travels in the film of refractive index mu along the path, that is BF and FD. So the geometrical path difference between two rays is BF plus FD minus BH. Okay, now we need to calculate the optical path difference. Optical path difference. The optical path difference is equal to mu L, that is, sorry, you can write directly. That is mu of air, that is mu of glass. In the triangle BFD, angle BFG is equal to angle GFD is equal to what? So BF is nothing but FD. So BF is equal to Fg by cos R, that is T cos R. So BF thus FD is equal to 2t cos r. Okay, so here we see that BG is nothing but GT, so the B, that is BD is equal to 2BG. Okay, and BG is equal to what? That is FG tan r. So is equal to okay, that is T tan r. অতএব BD is equal to 2T tan r. So in the tribus, in the triangle, in the triangle, BHT is the angle HBD is nothing but 90 degree minus I. BHD is equal to 90 degree, that is 90 degree. So BD base is equal to I. So BA is equal to BD sin I is equal to 2T tan R sin I. Now from Snell's law, what is this? That is sin I is equal to mu sin R. So ultimately BH is equal to 2T tan R into sin R. There will be mu, so that is 2 mu T sin square R by cos R. Okay, so putting this BH what we have, that is optical path difference, that mu 2T cos R minus 2 mu T sin square R by cos R. Is equal to 2 mu T, that is common, process cos R. So that is the optical path difference of for the interference of reflected beam. Now there we have a correction. We have to do this, so we can write down this point, the correction for what, and account of phase difference, that is phase change at reflection, that is because the light is reflected, that is the denser medium, that is air, that is rarer medium, so there is extra pi phase. So for that we have to add or difference the lambda by 2 path change. So now I am not writing. Okay, this when a ray is reflected at the boundary of a rarer to denser medium, a path change of lambda by 2 occurs for the ray BC. On the other hand, this light is reflected here, so there is no phase change because this is a denser medium, rarer medium. So for that case, there is no path difference. So there is no path difference due to transmission at D. So the correction is, so the optical path change can be written as, that is Newton cos R lambda by 2. So, now condition for maxima, that is brightness actually, and minima, that is darkness. So maximum is brightness and okay. So maximum occurs when the optical path difference becomes m lambda, where m is the integer. So maximum occurs when 2 mu t cos r minus lambda by 2 is equal to m lambda, where m is an integer. So 2 mu t cos r is equal to What can I write? Okay. So this is the condition of maxima brightness. Okay. Similarly, the condition of minimum. So when this optical path difference become the odd multiply of lambda by 2. So 2 mu t cos r minus lambda by 2 is equal to 2n plus 1 lambda by 2. So 2 mu t cos r is equal to, that is n into lambda. Okay. So actually n plus 1 you can write down. Why we have omitted the 1? Because the phase relationship of the interfering waves does not change if one full wave is added or subtracted from any of the interfering waves. So therefore m plus 1 can be written as n.